Now you just binge watched around 8 hours of Netflix, and how does Netflix know exactly what to recommend next? The answer processes 450 billion events per day. Now imagine your Netflix. Every second, billions of users are watching, pausing, and rewinding. That's petabyte of data. You can't process this in real time for recommendations because your servers would melt. Now, this is where batch processing saves the day. If you're interviewing at Man, then they will ask you about this question. Today, we are going to deep dive into batch processing and distributed systems, the backbone of every major tech company. By the end, you'll understand how Google, Meta, and Amazon process data at planetary scale. Okay, guys, let's start with some basics. Batch processing means processing large amount of data in groups or maybe batches. The batches can be of 1 day, 1 minute, 5 minutes, depending upon the requirement, rather than doing one by one. So if you see here in batch processing, we collect the data for some time. So we are collecting data first, we'll wait for the prescribed number of time. And once we have waited, or we have reached the threshold. So for example, if we collect data for 5 minutes, 5 minutes happen, then it will start the processing. And then when the processing is done, there we will receive the output. Now in real-time processing, for example, a credit card transaction, whenever you pay some money, it will do instant processing of the data and the response also will be instant. You understand the difference. So in batch processing, we collect the data for some time, whereas in real-time processing, we instantly do the reply. So there are different pros and cons of both the approach, and it's not that we have to use real-time all the time or we have to use batch processing all the time. It depends upon the scenarios, which I will explain you a bit later. Okay, now think about your credit card statement. When you swipe the card at Starbucks, right? That transaction is processed in real time, then it is approved or it is instantly declined. But at the end of the month, your bank processes millions of transactions together to generate a statement, to detect fraud, or to calculate the rewards. Now, that is called batch processing. You must have seen that you get the statement, and based upon that, your reward points are also calculated. In that scenario, we have to do batch processing. We cannot do real time processing in that case. Now, you get the difference when you are supposed to do real time operation and when you are supposed to do batch processing, right? Now, guys, do you know that a 40-year-old Unix command can outperform your fancy Python script? Here's why Google is still using it. So before we jump into distributed system, let's talk about the Unix philosophy. You know, these commands like grep, sort, awk, they're not just for sysadmins, they are the OG bash processors, and understanding them is the key to understanding MapReduce. According to the Unix philosophy, we do one thing well and then compose tools together. This is the foundation for all modern technology and batch processing. Let's analyze a log file. Say you have billions of web server logs and you want to find the top 5 visit pages. Now, what we will have in this case is, let's take a command. We'll do cat access.log. Access.log is the log file. Then awk print $7. Print $7. 7 is the location of the URL. Basically, we're trying to find all the URLs that have been called in the logs. Then we will do sort. Then unique-c sort-rn head -5. Let me explain you the meaning of all these commands and then we'll go over it. Cat runs the file. Then awk awk extract the URL in column number 7. The sort command groups the identical URLs together. After sorting it, we want to find the unique counts. So for that, we put unique-c. That will find all the unique URLs along with their count. Now, after that, we want to sort it again because we want the highest number on the top. So this time we will do a different type of sorting. Here we will do sort-rn, where we have already mentioned here. This time now we will have the top number of appearing URL on the top and the lower count appearing at the lower. And then after that, we want to extract top 5. We are not concerned with all the count. We just want top 5. So then we'll put head-5. That way it will extract the top 5 URL. Now, do you notice a pattern here? Each tool does one job here. The pipe operator change them. You see the pipe operator here in red, this one, this one, this one. So the pi operator changed them. This is exactly how MapReduce works in distributed system. And the beauty is this process can churn gigabytes of data on a single machine. But what about petabytes of data? This is where distributed system comes. We'll do parallel processing in them. So let me just go back to your log page and show it how it looks like. So we talked about this log page where we have at line number 7, at column 7, we have the URL. So first it goes to the awk, which collects all the URLs here. Then it goes to the sort because we paid the sort command after awk. So it's a pipeline process. The next pipeline of sorting starts. So here it is sorting according to the alphabetical order. Now after that, we wanted to group it together and find the unique URLs. So that happens in a pipeline fashion. As soon as the sorting is complete, the next thing happen is finding the unique URLs with the count. So if you see here, we find the unique URLs and their count. About is occurring 1 time, home is occurring 2 times. Now I only want top 5 occurring URLs. So what I do is reverse sort. So I'll do a reverse sort using -rn. Now the number of URLs occurring the most number of times will be on the top. And then the lower one will go at the bottom and I'll have the top 5 URLs used. This is how a typical Unix flow happens. From here on, we'll connect how MapReduce works. You get the point, right? The pipeline operation, how we select, how parallelly we can do the operations or sequentially also. But the main philosophy is when one process is done completely, properly, then only the next process happens or start. From here, let's connect MapReduce. Okay, and now here we are to the MapReduce, which is the basis for all the type of batch processing. Now, Google processes 20 petabytes per day with just one algorithm. And it is simpler than you think, and this is called MapReduce. MapReduce is like a Unix pipeline on steroids, distributed across thousands of machines. Now, there are primarily 2 phases, map and reduce, and that's it. Very simple. So, map phase is the transform and extractions. Like awk command in the Unix command, which we discussed previously, it just takes the input and emit key value pairs. If you see here, there are key values. The is the key, 1 is the key. I'll take this example in detail. Let me just explain you the basics and we'll go deep dive into it a few minutes. Then the reduce phase. Reduce phase's job is to aggregate and summarize. Like the sort and unique function which we used in the Unix command, its job is to group by key and then combine the value so that it can be used later on. Now let's do a quick example of this word. The input is the quick brown fox jumps over the lazy dog. What does MapPhase does? It splits the sentence into different words and emits the number with it called 1. So every word like the, quick, brown, fox is being emitted with the number 1. This is the job of mapper. Plus point is we can do this job parallelly. So it is not required to be going through only one machine. It can be done parallelly. So that is how we can make it faster. Now after this, we have the shuffle phase. Shuffle phase is very critical and very important because here the grouping happens and the sorting happens. Now if you see all the, we have 2 times the, here and here. We are grouping it together in all the systems. Wherever the mapping happened for 2 different the's, they will be grouped together. If you see here, we have grouped the together. We have grouped all similar word together and also sorted them in alphabetical order or maybe according to the key. Not only alphabetical, whatever is the key, we sort them accordingly. So if you see, all of them are sorted here. This is a very expensive stage where a lot of computation is done. And another point is that this phase cannot be done in parallel. It has to be done in one single machine. Although that is a drawback, but we have to do it because how we will do the reduction then? We have to group them. So there is no way out of it. And the third phase is the reduce phase. Here we calculate the sum. Now, if you want to find the word count, in this case, we will do the calculation. Now we've already done the grouping. Reduce phase is simple. We can do it in parallel also. In every machine, we just send the groups and do the calculation and emit the output. Now, if you see here, D has the output 2 because it occurred 2 times. Others had an output 1 because it occurred one time. Similarly, other words count can be calculated and done the aggregation and then emitted output. Now imagine this across 1000 machines, each processing a chunk of data in parallel. That's the power. The key insight is MapReduce is embarrassingly parallel. No machine needs to talk to one another during map or reduce phase, only during the shuffle phase. That's the power of MapReduce. Now let's do a bit of deep dive into MapReduce system. And this one optimization can make a bad job 100x faster. Now Amazon asks this in every data engineering interview. Now here's where it gets interesting. You've seen in databases that you have different types of joins like inner join, outer joins, right? Now in distributed batch processing, how do we join? There are different types of data and they might be correlated also. There's a high possibility. Like for example, in Amazon, you have a user database. Then you have the shopping order item, order list of all the users. How do we connect them? Right? We need to connect them to find out how many orders they have done, what is their monthly consumption, what is their monthly expenditure. How do we do about them? How do we connect the distributed data together? Now there comes this join strategy in batch processing. This is especially important for distributed systems. You might also use it in other systems, not only in batch processing. So here are three strategies: reduce side, map side, and partition join. Okay, let me take reduce side join. Assuming we have two data sets. One is a user database, which has users information, and the second has a data of user expenditure or the orders done by users. Now we feed both of them together in the map phase. And then what we do is we just emit the values. So user 1 has user ID 1 for the user information. For the orders, we'll do user 1 has order 1, order 2. So we are emitting all kind of data for specific users, right? Now comes the shuffle phase. In the shuffle phase, we combine all the type of data of user. So the first data set here was the user information. The second data set was the user orders. So we combine both of them. So user 1 will have user information plus the orders which they have done. This is the combination phase. And this is quite expensive because we are combining different sets of data and they are different type, not they are similar type. We need to find a meaning also out of them. So that is why here we do the join. This is the shuffle phase. And then reduce. Reduce is pretty simple. We just collate, aggregate the data, find the meaning out of it, and then emit it. One negative point about it is that we use a lot of computation in the shuffle phase, and we cannot even do it parallelly because we need all the data together, right? Next is map side join. Now the map side join is used when one of the data or either of the data is a small data set. Because there are cases, because the users might be 100, but the orders can be thousands and 10,000. You see, 100 user data set is very small. So what do we do in that case? I was thinking about it. Why don't we store it in one of the partitions? Or why don't we store it in all the servers? Because this is such a small, 100 users is such a small. I mean, in real-time cases, there might be 10,000 or 1 million, but the data set for the orders might be exponential. So why don't we store a small data set in the map server itself? That way I don't have to do a shuffling again because I already have the data. I just need to combine what all order IDs coming or emitted by the mapper. You see the advantage. The shuffle automatically goes away from here, right? So in this case, significantly reduce the network hops and network partitions. The speed becomes very high, but the memory usage is also high because we are now storing the data within the memory. It is good for small data set which can fit the memory. The third part is the partition join. So in this case, the data is already partitioned. If you don't know about partitioning of data, please check out my partition tutorial in the other video. Let me give you a gist. Partitioning is user starting from A to M in one partition, user starting from N to Z in another partition. So we know that all the users starting from A to M will be in one partition. So we are not caring about other users' data. So that is how we have partition data. And when it is a partition data, the job of MapReduce becomes much more simpler because the expectation reduces. It knows that only this set of data will be coming to me for mapping and reducing. So that way, we can also, combine it with a map side join when we have lesser data because the partition might be, we can easily store the data. Now here the advantage again is that network latency required is low. Speed becomes fast. Now here the memory is also low because we are partitioning the data. We need to store lesser amount of data. Now let's compare all the three strategies together. Shuffling is only happening in the reduce side. In map side and partition, we're not even using shuffling now. So it's only used in the reduce side strategy. What about the memory? We talked about how much memory is required. If we are storing some data within the servers, then some memory is needed. So in this case, in reduce, we are not using a memory, right? Because we are doing the calculation on the fly. But in map side and partition side, we are using memory. We are storing the data. Now, how much memory is required? In map side, we are storing all the data in the memory. Wherein in partitioning side, we are storing data, but it's low because the data is partitioned. So that is why high memory need is there on the map side and low memory need is there on the partition side. What about the speed? The fastest is map side and partition. And if we compare the use cases, if we have small data, we should use map side. If both the data are large, then we should use reduce side. Now, if you're getting already the partition data, we should use partition strategy. Now, in interviews, whenever you are asked such questions, you should always ask about the data set size. If one is small, then broadcast join wins. If both are used, either use reduce side join, or if it is pre-partition, then you can use partition side. Let me give you an example. In Meta also, switching from reduce side to broadcast join of user profile enrichment reduced the job time from 4 hours to 15 minutes. That is a magic. So now you know how these partitioning or data strategies are really important for your batch processing. Now I'm sorry to break you this, but MapReduce is dead. Here's what Google, Netflix, and Uber are using instead. MapReduce has a fatal flaw that is called materialization. After every map and reduce, it writes the result to the disk, and for multiple stage job, it is painfully slow. If you see here, after map, we write it to the disk. After reduce, then we write it to the disk. Then again map, we write it to a disk, and then again output, write it to the disk. Write to the disk, 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 disk. Cycle is repeating again. So it makes it slow because the disk IOPS is very slow. Reading from the disk is also slow. So then we got introduced to some of the latest technology which is in the market nowadays. Let me show you how Apache Spark works. This is the modern day data processing application. We transform the data, store it in memory. No need to store it in disk. Then we again transform the data, again store it to memory. Reading and writing from the memory is much faster than from the disk because after all, we are not going to store the data, we have to get rid of it. So why do we want to store it in a disk? Because this is a temporary intermediate data and we don't need to store it. We can just get rid of it. We need only the final output data to be stored. So that is why this Spark frameworks makes it much faster. Let me show you some of the frameworks nowadays which are being used. Okay, so we have a couple of frameworks nowadays. We have MapReduce, Spark, Flink, Beam. If we consider MapReduce as 1x, it should be used for simple jobs, not complex jobs. Nowadays, we need faster processing. Although it is not used anymore in the latest system, but legacy systems are still using it like bankings and other applications. So it is still used, but not used in the latest application. We have two new technologies that have been used for quite a while now. One is Spark and another is Flink. Spark is 100x faster. It is used for iterative jobs. Uber, Alibaba, they're using it. Then Flink. Flink is 50x faster, but it is used for streaming processes. Streaming is live data, real-time data processing, like Spotify and LinkedIn. There you need real data, real-time data. So these are the two use cases. If you want to use batch processing, we use Spark. If you want to use streaming, we use Flink. These are the two primarily used applications. What about Beam? Now, Beam has been introduced latestly by Google. It is used by Google. The main use of Beam is it is combined batch processing and real-time processing into one unit so that we can reduce the amount of memory, space, and we can increase the speed. It's still not used much in many applications. What I've used currently is Flink and Spark, but it is coming. Let's see how it goes in future. Now, for those who don't have much experience or who are new into this industry of data processing, I'll go a step back and show how the evolution happened. In 2004, MapReduce was introduced by Google, where it was used by all the search pages. The ranking was done based upon MapReduce. It was a very promising. But the only drawback was too much space, too much disk was required, too much memory was required, and that actually was a drawback out of it. Then in 2014, some of the scientists at Berkeley came up with a function where they said, why don't we use memory instead of disk usage? This will drastically reduce the memory usage, it will increase the speed. There they came up with a framework called Spark, and now it is known as Apache Spark. It was a revolutionizing idea. We used Spark everywhere. And soon in 2016, some data artisans came up with Flink. The same concept and similar concept was now being used for real-time data as well. So why don't we use memory? Spark and Flink both are under Apache banner, but they've solved a lot of problem, makes it easier to process the real-time and the batch data faster. What about 2026? We have been by Google. Still promising, much faster, lesser memory usage. But is this the future? Let's see who can tell about it. But it is just 2026 and we still need to wait at least 1 year to see if that will change how we use Spark and Flink. Now let's take another question. This exact same question was asked at Google at L5 interview level. Here's how to nail it. Let's put it all together what we have learned so far in this question. The question is, design a system to process 10 TB of web crawl data daily and find the duplicate content across the website. Now, how would you approach this? Now, this is a classical batch processing design question. Now, here's how to structure your answer. Step 1, we go on to the clarification question. We will ask how many pages? Let's say 100 million. What defines a duplicate? Let's say if it is 90% similar, then it's a duplicate. What about the latency requirement? Because that is very important. If we don't talk about latency, how we'll figure out if it's like asynchronous or synchronous? So in that, based upon the latency requirement, we can come about the daily batch job frequency. We can cover the results, what will be the frequency, like 5 minutes or hour or daily, right? Then step 2, we move on to the high-level approach. We should quickly work about it, the high-level approach, because we need to deep dive into some of the applications. So step 2, we'll talk about the usage of batch processing and not real-time, because this is the duplication removal. Then we'll talk about the databases, what we'll be using. In this case, we will be using HDFS and S3 because it can store tons of data. Then we'll talk about the process, what we'll be using. Since Spark is the latest process, we will use Spark. Now, step 3 will be falling onto the algorithm. We can talk about the algorithm, what we'll be using. First, we will parse the HTML and extract the text out of it. That is the most crucial and the initial step. Now, after that comes the main challenge. How do we find the duplicate? How we will do the MapReduce strategy? So what we can do is, first we can create a hash out of it using a sim hash and then create a fingerprints out of it. Let me explain you sim hash in detail and then we'll proceed next. Quickly going on to the sim hash, suppose we have a document or maybe the HTML page that has the quick brown fox example which we used previously. The hash will be something like this, 1011. It will be in binary format. We can use any key like SHA, RSA, whatever we like. And then we want to group similar hashes together so that we can create a map phase and reduce phase out of it. And it makes sense also to group together related data instead of comparing each and every text with each other. That will make it super slow. Now to optimize it, we should group together. And how do we optimize that? We take the prefix, the first 4 integers out of the hash. Because the last 4, the most significant bit, will tell us if they are related or not. So based upon that, we'll group together with similar prefixes and then compare them in the group. Now let's fall back to the algorithm which we were discussing. Now after finding the sim hash and the fingerprints and then grouping them together, we can group them together. Now after that, we can talk about the optimization. We have done the algorithm, we need to optimize it now. So for optimization, we can use a strategy which we discussed about MapReduce, how to join different type of data. We can use the partition strategy, or if the data is small, we can use the broadcast strategy. Then we can talk about how much time will it use for hash creation. It will be ON per document. And then what will be the amount of time it will be used there. So these are some of the things we can talk about. Next comes the scale. Scale is very important in system design. Along with optimization, we'll be dealing with terabytes and petabytes of data. So we can talk about how many machines will be required. So for example, if we have 10 TB of data and there are 1000 machines, we can distribute equally 10 GB per machine. Then we can talk about what will the cost of comparison. Usually comparison costs around n square amount of time, and the total amount can come out around 2 hours with proper partitioning. Now the key to interview is always mention the trade-offs. Whatever strategies we are using for batch processing, always mention the trade-off. Something like we could use exact matching for speed, but similarity detection catches more duplicates at higher computation costs. Something like this, and you should not only this, but you should also discuss the other phases also. All the trade-offs are very, very important. And that's how a system design interview should go like. All right, so let's recap what you've learned today. We first learned about batch processing basics. We learned about the trade-offs, the latency throughput. Then we started with the Unix philosophy. We learned about how we collect data in a Unix command and then mapped it to a MapReduce foundation, where we connected how a Unix philosophy is related to a MapReduce foundation. Then moving forward, after telling the basics about MapReduce, we discuss about some of the join strategies, because there are cases where we need to join data from different data sets together. And how do we do that? There we discuss about different join strategy like reduce join, map side join, reduce side join, or partition join. Then moving forward, we discuss how people are moving away from MapReduce to latest technologies like Spark and Flink and Beam, because they give us appetite to do more processing. They makes easier processing. Instead of using disk, we use memory, and then it becomes faster. We also use streaming nowadays because the technology has moved from batching to streaming nowadays. Although batch processing is still relevant because we need to do analytics, we need to do recommendation system, there it is mostly used. But some of the use cases need streaming more than batch processing. So we discussed those trade-offs and the different technologies that are coming nowadays. And then finally, we discussed where in interviews it will be useful for you, where you can face a question related to MapReduce or batch processing technology. We discussed how we will crawl a lot of data, 10 TB of data, and find duplicate of them, where we found out, okay, how batch processing helps, how deduplication helps. All right, so after discussing all this, guys, if you're preparing for FAANG interviews, practice designing batch systems like recommendation system, fraud detection, log analysis, data warehousing. Next video, we're going to deep dive into stream processing, the real-time counterpart of batch processing. So subscribe if you don't want to miss it. Drop a comment if you have used any of the batch processing strategy or you are stumped in an interview when a question came related to batch processing. Thanks for watching and good luck with the interviews.